Alright, so this is active filter design, lecture 25. So far we have seen how to derive transfer functions, how to implement them using transconductors, and then we saw how we will order the biquads, and then we also saw how one can implement an LC ladder network with transconductors. The aim being to be able to get the very desirable low sensitivity properties of the LC passive LC ladder network when using active elements. Okay. So we will, what we have not seen is how to realize high pass, band stop, and so on. They are actually quite straightforward, as we will see later on. But at this point, let us continue on with the real business now of implementing transconductors with transistors. We have already seen in the previous assignment that if you have a filter, in assignment 4 you designed a second order filter using CMOS inverters, right, and you also saw that if an active filter will have power supply, a ground, an input voltage and an output port, okay. Right, and in one of the parts of the assignment you must have seen that if the supply voltage is noisy, for example, this VDD was not clean, but there was a disturbance on VDD, okay, then what did you see at the output? What did you see? So you not only do you see a filtered version of Vin, but also plus whatever so called noise on the supply, also filtered, but with some other transfer function, correct? Okay, and due to nonlinearities in the filter, it is also likely that this tone at the input tone and the noise tone will get multiplied due to the nonlinearity and get all sorts of weird stuff happen, correct? The stuff in the assignment is somewhat exaggerated. How much noise did you put in your assignment on the supply? 10 millivolts. What was the input? 100 millivolts. Okay, so maybe 10 millivolts of noise is perhaps it's not too far fetched, right? But it's not too small either. But you would have seen most dominantly that the output should be only consisting of the input and the input frequency and the frequency at the noise in the supply voltage. The mixing terms would have been much smaller than either of these terms. So to first order, you can say that the noise on the supply through some other transfer function is coming to the output. Now, is this a good thing, do you think, or bad thing? Why is this bad? Why is this bad? And the whole idea in putting a filter is the input has got some quantity which you want and some you don't want, right? And the point in putting the filter is that you want to get rid of the stuff that you don't want. Now, because of noise in the supply, right, you are getting rid of one kind of stuff that you don't want, and now adding something else which you also don't want, and this being noise from the supply. Okay, so that is definitely a problem. Another thing is, then one might argue that, oh, maybe this assumption of noise in the supply is a bad one, right? If you make worst case assumptions, very, very bad assumptions, then you can come up with all sorts of worst case scenarios, right? Right now an asteroid might hit us and we might all be dead, right? The next moment, right? So nothing has happened, you understand? So that's a theoretical possibility. And in principle, you can protect yourself against this kind of thing by sitting in a lead enclosure and blah blah blah, and 40 feet under the ground, right? But you don't do that because it's a very far-fetched situation. So like that. Now, is this this noise in the supply, is this a far-fetched situation, or is it, do you think, a reasonably practical scenario? It's reasonably practical simply because this filter most of the time is not sitting in a showcase. It's being used as a part of a big mixed signal chip, right? So as I indicated to you in the very beginning of this course, this filter is a part of a big chip. Perhaps there's a lot of analog, there's a lot of digital, and this is all part of the signal conditioning, so-called signal conditioning electronics, right? So you have some filter, right? Then some A to D, and then some DSP and so on. Okay. So this whole chip is operating off of some supply, right? So one way of doing this is to run common supply rails, okay, to the filter, to the whole chip, okay, and the same ground rail for everything, and then this goes to the battery. All right. So this is the chip. Okay. Now the DSP is running is a whole bunch of gates, right? And we'll probably be needing a master clock from outside, all right, which goes to the DSP, also to the A to D converter, because the A to D converter needs to figure out when to sample. And perhaps the clock is not directly sent out, perhaps you want to multiply up the clock frequency by some number and then send it to different blocks, but this should serve to illustrate the point. Now, as you probably have all seen, a logic gate most likely is being implemented using CMOS, and a CMOS gate, for example, the CMOS inverter, when used as a NOT gate, when does it draw current from the supply? When the transition from 0 to 1 occurs. So even though you have not seen, those of you who have not undergone a digital IC class, you should be able to understand if I say that given that a NOT gate consumes power only when it sees a 0 to 1 or a 1 to 0 transition, right? See, in a similar fashion, any logic gate built with the CMOS family will also draw current in spikes from the supply only when it sees transitions. Okay, so that's fine. Now, given that we understand this, it then follows that the digital part of the chip, for example, will be drawing current from the supply in the form of spikes. Okay, the exact value of those spikes depends on the number of gates and what the DSP is doing and all that, but it must all be in the form of spikes. Okay. Now, ideally, what have we assumed when we did all our filter calculations? What have we assumed for the supply? We have assumed that it is a constant, right? In other words, it's incrementally ground. Correct? Now, if the battery was perfect and had zero output impedance across all frequencies, then what can you say about the supply voltage? If the battery is ideal and has got zero output impedance across all frequencies, why am I stressing the word all frequencies? See, please note that this is the battery. All right, there is some output impedance Z out, okay, and the load the battery is driving can be thought of as a current source, right, which is demanding current in the form of spikes, right. So this current is impulsive, right? This is the load. Okay. Now the voltage here as a function of frequency will be what? What will this be? V bat minus Z out of F times IL of F. Correct? And of course, IL of F will have a DC component that corresponds to the average participation of the DSP. But it also has components at predominantly at which frequency? At the clock frequency. And why is that? At every clock transition there is stuff happening, right? So there will also be components at the clock frequency and its multiples. Okay. So please note that it is not just sufficient that Z out be 0 at DC. You understand? Okay. Alright. It must also be 0 at F clock and all its multiples. You understand? Why is that important? Okay, now that there seems to be some, let me give you an example. Let's say this is V bat. Let's say Z out is an inductance. And I am now drawing spikes of current at Fs. Okay? You understand? So what is the DC voltage at this node? V bat. Why? Because the DC value of the inductor is the DC voltage drop across an inductor in steady state will always be 0. So this DC voltage will always be V bat. Okay. However, what can you say about the instantaneous voltage here? Whenever the current in the load attempts to become a spike, right? What are you in essence trying to do? You are trying to suddenly change the current through the inductor, which can only happen if you have to effect a step or an impulsive change in current through an inductor. What must happen to its voltage? Right. It must go to infinity. Right. In fact, it's a derivative of an impulse is the voltage. Correct. So you will therefore find that this voltage is on the average V bat, but instantaneously it is jumping up and down by very, very large amounts. Correct? Okay. Of course, now you can argue that the currents are not really impulses because the real impulses are impossible to generate. It's probably a very high current for a very short amount of time. Okay, it's a narrow pulse, but that still doesn't change the. Then it will just happen that the voltage here V bat plus okay, the voltage there across the load is not doesn't have these spikes which go to infinity but become very, very large. You understand? Okay. So what and why am I calling this noise? Well, when we really don't know the exact statistics of this of these pulses, you might as well say noise, right? In principle, if you know the input to the DSP, you should be able to predict what current it will draw. So that way, it is indeed deterministic. But as far as the filter is concerned, it's probably completely uncorrelated with what the filter is processing. So you might as well call it noise. So in other words, what happens at the supply is that you can always expect the DC value to be what you want, but there will be some fluctuation, right, at especially when there is a lot of digital logic on the chip. Okay. Now, one might ask, how realistic is this scenario? Okay. The answer to that is that any voltage source will always have an inductive component of output impedance, right. Even if the battery was ideal, by the time you take a wire and route it through the bond wires on the chip into the chip, right, through that package and so on, you will always pick up inductance. So, it is not really hard to pick up inductance at all, which means that this voltage being constant is in fact a very bad assumption to make. The only thing, in fact, a reasonable assumption to make is that the voltage has got a constant DC value, but has got a lot of, as far as you are concerned, random noise hovering around the average, correct. So, indeed this scenario is something that can definitely occur. What do you think you can do to fix this to some degree? What is the problem? The problem is that the battery has got an inductive output impedance, right, which means that if you attempt to draw spikes of current from the battery, you will see a big dip in the voltage. Okay, so you need somebody to provide those spikes, and what do you think? You can put a capacitor, right. So, a fix for this problem is to put what is called a supply bypass capacitor. Okay. So, what happens to the impedance looking in here now? At low frequencies, what is it? At low frequency, it is 0. Okay. If the only the inductor would be there, the impedance would keep increasing with frequency, right. If only the capacitor was there, what will happen? It will keep decreasing with frequency. Okay, this is the L, this is the C. So, what if now both are in parallel, what do you think will happen? The combined impedance will probably look like this. You understand? Okay. So, you can see that at very high frequency there is no problem, at very low frequency there is no problem. At the resonant frequency of the L and C, there is a possibility that the stuff will go to infinity because the parallel LC network. In reality, it turns out that there will always be some damping resistance in the form of loss, and the effective impedance will probably be something like this. Okay. So, if you make the bypass capacitor larger and larger and larger, what do you think will happen to the impedance? Two things happen. The frequency at which the L and C resonate come lower, and what happens to the peak impedance? Will also come down, correct. So, in principle, by choosing a very large capacitor between this point and ground, okay, you can make the supply output impedance be as low as possible. However, this is not a practical thing because please note that this capacitor must be on chip, correct, because this inductance here represents the length of, the inductance of the entire wire running from the battery all the way to the internals of the chip. So, this whatever bypass capacitance you add must remain on chip. So, it becomes impractical to make it very large. Pardon? No, ground is always a reference potential with which you measure everything else, right. There is nothing called absolute ground. It is all with respect, It's all some potential with respect to which you measure everything else. You understand? So, if all your circuits are running between the two plates of the capacitor, right? If all your circuits are running between the two plates of your capacitor, the fact that the lower plate of the capacitor is jumping up and down is completely irrelevant, because your circuits are running only I mean, as far as your circuits are concerned, right? Okay. All right.
And so the digital logic is after the feedback, that is why it is affecting the feedback. So, like if we connect the VDD to the left side, like how it will go.
Oh, not really, because the okay, the argument was that, okay, here in this diagram it looks like the filter is getting connected to the supply after the digital logic. So, don't you think it will help if instead of having the battery here, I put the battery here? Any comments on this? When do you think this will help and when do you think this will not help? Pardon? So, if the inside wire is dominating, then this will help. However, do you think the inside stuff will dominate or the outside stuff will dominate? The stuff outside will dominate. I mean, though I draw it like this, in reality, the internals of the chip will be very small and the external of the chip, this part, is going to be very, very large, right? So, if this inductance dominates, which is what will happen in practice, right? Whether you bring the supply, route the supply there first or here first, makes very little difference. In practice, going forward, one could say it doesn't make sense to route supply like this. Perhaps you route supply separately to the digital logic as well as to the analog part, and you join them together only outside. Okay, now this is digressing from the main theme, but I will just do it since I mention it. Okay. So, let us say this is the analog, right? This is the digital, which is going to draw spiky supplies, I mean spiky current. Okay. Now, if I did this is bad news. This is not a very smart thing to do, because the analog and the digital share the same supply. Now, a smarter thing to do would be to bring the analog out separately, correct? The digital out separately, okay, and join them on the, so this is the board, or rather this is the chip boundary, okay. So, you route the supplies to the analog and the digital portions separately, and you put bypass capacitors here, here and here. Why does this make more sense? Basically, this voltage is quiet, okay, all right, and what happens to all these, the spiky current, please note, is coming from where? This part. Where does all that go? It all goes through this capacitor, okay, because that's got the lowest impedance at high frequency. A very small portion of it will go here, right, and most of that will go through this capacitor, correct. So, this voltage drop at high frequency will be even smaller, correct. Now, that is getting filtered through this LC network, and the voltage drop across this capacitor is even smaller. You understand? So, this is common practice whenever you want to do analog and digital parts on a chip. It does not make sense, especially if your analog is very sensitive, to tie the analog and digital supplies together on the chip. It makes sense to bring them outside and then tie them together on the board with appropriate bypass capacitors. Please note that putting large capacitances on the board, right, is a inexpensive affair, no big deal. Whereas if you were to put a big bypass capacitor on the chip, that would be a problem. Okay. All right. So anyway, the bottom line behind this whole discussion was that one cannot avoid supply noise. And so another thing that we found, or rather you found through doing the fourth assignment, was that supply noise finds its way to the filter output, and this is obviously a bad thing. So as you discovered in your assignment, what is the solution to the problem? So one solution to the problem is to say, I will take a filter, I will make a copy and paste version of this, okay, and the supply is common to both the filters, and if there is noise here on the supply, it does not bother me anymore, because V input plus, Vi minus, Vo plus and Vo minus. So now I say my input signal, right, or the signal which I am interested in, is not VIP nor is it VIM. My input signal is encoded as, or is represented as, the difference between VIP and VIM. So the input is VIP minus VIM, right, and the output is not VOP nor is it VOM, it is VOP minus VOM. Okay. Now what is the advantage of doing this? Because the noise on the supply, right, because these two filters are identical, the transfer function from this noise source to this output and the noise source to this output must be the same as long as the two halves are identical, correct. So when you take the difference, the noise component goes away completely. Does it make sense? Okay. So this way you avoid supply noise, or in more general terms, you apply noise, you reject all disturbances or noise sources which are common to both halves, correct. In other words, you avoid all disturbances common to both halves. Is that clear? All right. Now this has now become a standard principle in all analog systems, right. So this is called differential operation. okay, where the quantities of interest are no longer the individual node voltages or the individual branch currents, but the difference between node voltages and the difference between branch currents. Okay. So, each one of these halves was called the single ended filter. When you put two together, it becomes a differential filter. Does it make sense? Okay. So, let us spend a couple of minutes understanding have we gained anything or lost anything as far as dynamic range is concerned. Okay. So, what is the one thing that we are seeing is that due to differential operation, what has happened to the power? Power has gone up by a factor of 2x. What about area? Has gone up also by a factor of 2x. What has happened to the dynamic range? Why? What has happened to the peak signal? What has happened to the peak signal strength? It has doubled. Why? Earlier the amplitude on each side, each arm was A, so the signal power was proportional to A square. Now if this is A, the other end is going minus A, so the peak signal amplitude has gone to 2A, which means the peak signal power has gone to 4A square, which is a factor of 4 larger than what we had earlier, right. So, signal power has gone up by a factor of 4x. What about noise power? Gone up, gone down? Gone up. Why? So, you have two filters, both of them are producing noise. The statistics of the noise will be the same, but they will be uncorrelated. So, what do you think will happen to the noise power? The mean square noise will be Vn1 square plus Vn2 square, which must be 2 times Vn1 square. So, this noise power must have gone up by a factor of 2x, which means that the dynamic range has gone up by a factor of 2, which is 3 dB. Okay. So, are we doing better or are we doing worse? There is really nothing to be surprised about. There is nothing to be surprised about, right? So, you are burning twice the power and you are getting 3 dB more dynamic range, which is a reasonable thing to do. Correct? The only advantage of differential operation is that you are now immune to all common mode noise. Okay. One illustration of common mode noise source being noise on the power supply. Right? We'll come. We'll going forward. We'll see many other noise sources. Is this clear? Okay. So, the building block of a single-ended GMC filter is a voltage controlled current source where the output current is GM times V. Now, what would then be the building block of a differential GMC filter? In a single-ended circuit, output current is GM times the input voltage. Pardon? So, the only difference now is that you no longer have one single input voltage and one output branch. You have two characters. One is VIP, VIM, and we have two output currents, right. So, the output, say I OP is GM into GM by 2, let's say, into VIP minus VOP, sorry. And this is IOM, which is GM by 2 into VIM minus VOM. All right. One very straightforward way of realizing this animal is to do what? If you had only animals like this, how will you realize this? Pardon? One way to do this, yes, people, come on, think, what can you do to realize this, given that you have that character there?
Using two branch connected block and connected outlets.
One way of realizing the differential operation is to simply use two single-ended halves, okay, which is exactly what you did in your assignment. You just copy paste an entire filter, run it with an inverted version of the original signal, correct, and then look at the difference between the outputs of the two filters. Okay. So this is, for example, VIP, VIM, GM, GM. This current is GM times VIP. This current is GM times VIM. Right, I'm sorry. Okay. And the difference between these two currents is GM times VIP minus VIM.
But we have common mode current on this.
Yes, you do. But if I am only interested in the differential parts, this is perfectly okay. Pardon? No, it doesn't. If I am only interested in differential stuff, how does it matter? No. They're all second order effects, right? In principle, you understand? In principle, this is perfectly okay. Alright? Okay. Now, let's move further. Before I go, I'd like to draw your attention to a couple of things. Given any two voltages VIP and VIM, I can always express them as a common mode quantity VIP plus VIM by 2 plus VIP minus VIM by 2, okay, and VIP plus VIM by 2 minus VIP minus VIM by 2. Correct? Okay. Now, this is called the common mode component. All right, and this is called the differential mode component. Okay. So therefore, we can write VIP as VCM plus VD, VIM as VCM minus VD, where VD is VIP minus VIM by 2. Does this make sense? Okay, this has got nothing to do with circuits. Any two voltages I can always express as average plus something and average minus something. Yes? Okay. Now, in our study on differential pairs in the basic class, we have seen a circuit where it not only amplifies the difference, but is also immune to common mode changes. Correct? And what was that? The differential amplifier, right? In other words, a differential pair like this if this is VCM plus VD and this is VCM minus VD, correct? And let's say we connect up these two drains to a sufficiently large voltage so that the transistors M1 and M2 operate in saturation. Then what can you say about the currents through M1 and M2 for small Vd? I1 must be equal to, or when Vd is 0, what are the currents? By symmetry, I0 must flow through both the transistors. So I1 must be equal to I0 plus Gm times and I2 must be I0 minus Gm times Vd. Is this clear? BTech students, you still remember all this from last class, or not last class but last course? Huh? Okay, so let me quickly refresh your memory. What is the incremental voltage here? 0, right? In other words, if VCM is fixed and VD changes a little bit, then incrementally the voltage at the node marked in green is 0. This, now a lot of it is jargon, this is called the source coupled node, okay, because in electrical engineering coupling means joining together, right? Okay, so here two sources are joined together, so this is called the source coupled node. And this is called the tail current source. All right. Okay. And what is Gm in terms of the parameters of the transistor and so on? The square root of, I mean, you can do it in many ways, is 2I0 divided by VGS of either M1 or M2, which all remain the same, minus VT, is also square root of 2, 2Ki and all that, right? Okay. All right. What is the quiescent value okay? What is the quiescent value at the source coupled node? Let us denote VGS minus VT as delta V, or the gate overdrive. Okay. So what is the quiescent voltage at the source coupled node? Okay, MTechs, PhD students, keep quiet. Let the BTechs answer. I've already said that the VGS minus VT of either transistor when VD is 0 is denoted by delta V. Is that visible at all actually, Ashwin, from there? Okay. Now can you tell me what the quiescent voltage is at this node? No, MS students please keep quiet. MTech students keep quiet. BTech students, Vivin, no calculation required. Yes? Correct, VGS, yeah, let's go systematically. What is the gate source voltage there?
VGS is delta V plus VT.
Very good, this is VT plus delta V. And when VD is 0, this potential is at VCM. So what must the source coupled node be at?
VCM plus VCM minus delta, yeah, minus VT minus delta.
Minus VT minus delta. Correct? Please note that this voltage can never be higher than this potential. Correct? Okay. I mean, physically, that means that the transistor must be off. M1 and M2 will be off then if the source is higher than the gate. So you should never stutter when the source voltage, even if you have some crazy doubt as to whether it is VCM minus VGS or VCM plus VGS. Okay, please note that the source voltage can never go above the gate, because we have assumed that, we've already said that I naught is flowing through both the transistors, which means that the gate source voltage must be positive. Okay. And how low can VDD go before the transistors go out of the triode region? To prevent the transistors from going into the triode region. Again, BTech students, VDD minimum is what? Pardon? Yeah, what is that? It's VCM minus VT. Correct? As long as VDD is greater than VCM minus VT, the transistors will be in the saturation region. Correct? Alright. Does VDD have to be greater than do transistors M1 and M2 have to be in saturation for the current to split equally? The question I am asking is it necessary for the two transistors to be in saturation for the tail current to split equally, or it's good enough if they are in triode? By symmetry, it doesn't matter whether the transistors M1 and M2 are in triode or in saturation, the current will always split equally. Okay, all right. And we know how to calculate the GM of the transistors. Does it make sense? Okay. Now, therefore, let's get back to our differential pair all over again. This current is VCM plus VD, VCM minus VD. All right. So, if VCM changes, what do you think will happen to if VCM changes, what do you think will happen to the currents through the transistors? Again, I am assuming that the drain current drains are connected to a high potential, so that both the transistors are in saturation. Nothing will happen. Why?
Both the potentials are dependent on VCM, I mean the gate and the source. So the difference will be.
Okay. So yeah. Okay. Fine. So what he's saying is that if the input differential voltage is 0, if I yank the common mode voltage up a little bit, right, the source node also goes up by exactly the same amount. And how did you establish that? Yeah, why? Tail current is constant also in the differential equivalent.
So the current is I naught. So VGS should be same.
Delta V will make the load is infinite.
I mean, how is this different from the differential situation is what I'm trying to get at.
Because it's the same current mode pass through both the machines.
Pardon? No, you keep quiet. You know, what you're saying is true even for differential mode operation, isn't it? Or no?
In a small signal common mode, the source voltage is VCM.
The source voltage is not VCM. I thought you just said that source voltage is VCM minus blah blah blah. Oh, small signal. Okay, so all right. When you're in doubt, always draw the incremental equivalent. Okay. You can please note that this can be split into a common mode equivalent half circuit. And how does that half circuit look like? This is the incremental VCM. Okay. How will the common mode half circuit look like? The current source will get split into two, and then the current source becomes an open circuit because incrementally it's an open, right? So what kind of controlled source is this now? Vivin, what is the incremental source voltage? This is the common mode incremental equivalent. It is a voltage controlled voltage source with an incremental gain of 1. So incrementally this also goes up by the same voltage, correct? Therefore, and whereas for differential inputs, what is the equivalent? That middle point will be ground. This is VD, and there is no point in drawing the other half because every node voltage is reversed in sign. And this current, incremental current, is GM times VD. Okay, this is just refresher. You're all supposed to know this. So in other words, the simple differential pair is a good candidate to start off with. Why? Because it is amplifying or converting the difference between these two voltages, right, into two currents. And what is the difference between the two currents? The difference in voltages is 2 VD, and the difference in currents is GM times 2 VD. Okay, so this is indeed doing what we want, correct? This is clear. Okay. So the next logical step is to say this current is I naught plus GM VD. This current is I naught minus GM VD okay. All right, and as we see, the differential pair is taking the difference between these two voltages and generating currents whose difference is proportional to the difference in the two voltages. Okay, but there is also a subtle difference, and that turns out to be quite important. Okay, when we just put two identical single-ended circuits, okay, for example, when we did this, if the input common mode changes, correct, what can you say about the output common mode current? Let me, okay, before I rush, let me point you to this thing. So, what is the output common mode current? Just like the common mode of two voltages is the average of the two voltages, the common mode of two currents is the average of the two currents. We have two currents here, I naught plus GMVD and I naught minus GMVD, and what is the common mode current? It is simply I naught. Okay. All right. And does this depend on the common mode voltage? The important thing is that this is independent of VCM. Is that clear? And why is this independent of VCM? Okay, blah blah blah. In other words, the differential pair, as we saw in the earlier classes, not only amplifies the difference, but it also has got common mode rejection, right? So in other words, it only amplifies the difference and is immune in principle to variations in the input common mode. Correct? Okay. So this is because good or high common mode rejection ratio of the differential pair. Okay. In contrast, what happens to this character? If I just took two single-ended halves, this is VCM plus VD and this is VCM minus VD, this is GM, this is GM. What is this current? GM times VCM plus VD, this is GM times VCM minus VD, correct? So what is the common mode current? It is GM times VCM, right? Please note that as far as differential operation is concerned, both of them are the same. However, there is a difference between the way they respond to common mode inputs. Okay, we see that this arrangement does not reject common mode at all, variations in input common mode at all. In fact, the gain for common mode is the same as the gain for differential mode. Correct? Okay. Now, why is intuitively speaking, why is this happening? Whereas in the differential pair, we see that in the differential pair the common mode is rejected. Correct? In other words, the common mode component of the output current is 0, or rather is constant. It does not depend on VCM at all. Yes. No. If the common mode decides the current, then the current must depend on the common mode, isn't it?
Yeah, but in the second case, you are having a higher current source.
Which case? So in the differential pair. What operations are we doing? Let me lead you to the answer. Right? What operations are involved when you want to subtract the two currents? You have two voltages and you have two currents. Okay. In the single-ended case, when you take two identical single-ended halves, you are converting each voltage into a current and then taking the difference. Whereas in the differential pair, what are you doing? First you are taking the difference and then converting that difference into a current. Right? Once you find the difference, the common mode is gone. Correct? So and you are converting this difference into an output current. So presumably the output current cannot depend on the input common mode. You understand? This is the fundamental difference between the two. Okay. So which do you think, obviously now no prizes for guessing, which do you think is a smarter thing to do? The first one is a good thing to do, because even though in principle the differential output is related to the differential input using through the same equation, the advantage of common mode rejection is that if you have any common mode noise source, it will not keep propagating throughout the filter, right? So the moment it encounters a differential pair, the output common mode is greatly suppressed, or rather the variations in the output common mode are greatly suppressed, or in principle 0, even though the input common mode is changing. You understand? Okay. So that is that. The next thing to do is to figure out what, is this, are we done, or the question is, do we need something more, is what we need to figure out. Anyway, as an aside, how do you think I'm going to implement the tail current source? So you put a current mirror of sorts and you're done. So this is VCM plus VD, so VCM minus VD. Okay. And please note, however, that what we wanted was a contraption like this. This is VCM plus VD, VCM minus VD. This is GM. You wanted some, what is this? GM times VD and minus GM times VD. Correct? What are we getting here? We are getting I naught plus GM times VD and I naught minus GM times VD. Correct? So what do we want and what do we don't want? We want the GM times VD, we do not want the I naught in both the currents. So what do you do if you have something which is sum of something you want and something you don't want, and you want to get rid of the something that you don't want? What would you do? You need to subtract I naught. Okay, so you have a current, you need to subtract I naught. So what law will you use to subtract I naught? KCL. So what do you think I should do? Conceptually, don't get into mirror and all this stuff right now. Conceptually, what will you do? I'll put Okay, so in other words, I need to get rid of I naught. So what I will do is to put a current I naught like this. This current is what? I naught plus GMVD, correct? So what is this current? Which way? Going in or going out? Animesh? Going in. Correct? Alright. Now what should I do here? Do the same thing. This is I naught. And what is happening here? What is this current? I naught minus GMVD. Okay. So what's happening? GMVD going out. Does it make sense? Okay. The question now is, are we done or is there some problem with this? Okay. Now let's see. So it seems as if everything is okay, right? Okay. Seems as if this will give I naught plus GMVD, this gives I naught minus GMVD. We are getting rid of the I naughts. Alright. So the currents coming out, if I now market this by putting all this in a box, it has two terminals and whatever. I mean, you can package it whatever way you want, right? All this is inside the box. It has two terminals, two voltage terminals, right? And namely this, and it has two output current terminals, namely this and this, just like this box. Correct? Okay, what is the only assumption we have made here, if at all? When will these equations be valid? When will these equations be valid? I naught plus GMVD and so on. Yes, Sandeep. Okay, small signal operation is one assumption. Another one? Assume that the output impedance of the transistors is infinite when they are operating in saturation. That's true. What else? What are the assumptions are we making? Current source is infinite output impedance. Sure, that's fine. That should be matched, yes. But is there a fundamental thing that we are missing? That's already what he said. I mean, VGS being incrementally very small is equivalent to saying small signal operation. The key assumption is that M1 and M2 have to be in okay. Please note that I played a little bit of a devious trick on you. All along we have said what did we say about the drains? We just assume that they are connected to a high enough voltage such that the transistors are in saturation. Okay. Now suddenly we said, oh, we don't want I naught, so we put current sources here. Okay. So I mean, it's not possible to have both, connect this to both a voltage source and a current source, isn't it? You want that current coming out. So the earlier picture of putting a voltage source here is no longer true. So now the onus is on us to make sure that the two transistors are indeed in saturation. Is this clear so far? Okay. The progression is very simple, right? We have a differential pair. One current will be I naught plus GM times VD. The other current is I naught minus GM times VD. We want the GM times VD or the minus GM times VD. We do not want the I naught. We need to therefore subtract I naught from both the branches. So a simplistic thing to do would be to put two current sources of value I naught, stick them in the drains, and what comes out is either GM VD or minus GM times VD. Now we need to figure out if the transistors M1 and M2 are in saturation. If they are in saturation, we move on further, correct? If they are not in saturation, we will figure out why and how to fix it, correct?
When the
Yes.
supply is shorted to a, like the drains are shorted to a voltage source, then it can be tried also.
As long as we said that the drains of, in the earlier example, we said that the drains of M1 and M2 are connected to a supply voltage which is sufficiently high to maintain M1 and M2 in saturation.
I thought you said it doesn't matter if
No, it does not. Okay, see, was the onus is now on us to ensure that M1 and M2 are in saturation, right? So first we'll have to figure out if they are in saturation. If they are, well and good, and we move on. If they aren't, we will figure out why they aren't in saturation and see what we can do to fix the problem. Is this clear? Okay. Now to figure out whether they are in saturation or not, what we could do, I suppose, I mean, if you are given this box, right, with two terminals at the coming in at the input and two at the output, what I would do to figure out if the transistors were in saturation or not would be to apply some differential voltage VD, okay, and measure the quiescent value at the output terminals. In this case, the drains of M1 and M2. And what do we need to know to figure out if the transistors are in triode or saturation? All that we need to know is the drain potential at M1 or M2, correct? Basically M1 and M2. And one way of figuring this out is to apply some VD. Okay, choose some arbitrary VD, apply it, and you look at the drain potentials of M1 and M2, and we figure out if that is high enough. And what is the meaning of high enough, Avinash? Yes, which is equivalent to, in this diagram, we must be greater than VCM plus VD or minus VD minus VT. In other words, the gate must be higher than, the drain must be higher at a potential which is higher than gate minus threshold, okay, or the drain can go at the most one threshold below the gate. All right. Okay. Now, so what we do is we will apply some convenient value of VD and check the potentials of the two transistors. If they are higher than gate minus threshold, then we are okay. All right. So what do you think is the most convenient value of VD to choose? I mean, what is the easiest value of VD to choose? You can choose anything. VDD. You guys don't like simple solutions or what? The easiest value of VD to choose is 0, isn't it? I mean, everything becomes symmetric and you are happy. Okay. All right. So, no. Okay, let me repeat that. No, what I said was, to figure out if M1 and M2 are in saturation, I'd like to choose some arbitrary VD, apply VCM plus VD on one side, VCM minus VD on the other, and determine the drain potentials at M1 and M2. Okay, and then we were wondering, is there what is the easiest value of VD to pick? Okay, you can pick anything, right? VD is 1 millivolt, 1.4 millivolts, 5 millivolts, E millivolts, everything, right? But it seems like the easiest thing to do is to pick VD equal to 0. Okay, I mean, definitely if M1 and M2 are not in triode for 0, it's a fat chance that they will be in triode for some other VD. Okay, all right. So, in other words, I pick the same VD, or rather, if I pick a 0 VD, this is 2 I naught, this is M1, this is M2, this is VCM, this is also VCM, because I have picked VD is 0. And what do you have in the drains? This is some large voltage. Okay, we don't have to worry about this at this point. I was talking about this character. Okay, what are the strengths of the two current sources? I naught, and this is I naught. And what are we interested in? We are interested in the potential at these two nodes. Okay. Now, because of symmetry, what can we say about these two potentials? They should be the same. So, for analysis, what we might as well do is analyze the half circuit like this, okay, with the understanding that whatever we come up with, whatever conclusions we come up with for this part of the circuit will also be the same for the other half. Does it make sense? Okay. So, the question is, what is we were trying to find out what the quiescent potentials here and here were. We have concluded now that the two are the same, and it doesn't make any sense to work with the full schematic. We will actually work with half the schematic. Okay. So, what is the current through this branch? 0 by symmetry, because the potentials are the same on both sides, no current will flow. Okay, great. So, can you comment on this potential now? We know that this current is 0, all right. So, if this current is 0, what is this current? I naught, all right. So, now can you comment on this potential?
Greater than VCM.
Okay. So, as far as we are concerned, the potential of this node is being determined by two current sources. One current source okay, I naught is attempting to push the node potential. This current source is attempting to push the potential of this node up, whereas this current source is attempting to pull the potential down, correct? So, if you have a node and the total current being pushed into the node is exactly the same as the total current being removed from the node, then there is no net charge accumulating on the node, therefore, its potential remains constant, correct? Okay. So, if two equal and opposite currents are incident on a node, then the node potential remains constant. Can we comment on the nature of this constant? We can't say anything about the node potential. The only thing we can say is that the potential remains constant. So, in principle, we cannot You understand? Is this clear? Yes? All right. Okay. Now, please note that what we assumed about this current source and this current source, they're ideal, okay, and we assumed that they're independent. In other words, this is one current source, that guy is another current source. Both of them are independent current sources, correct? And so, if you attempt to make two identical current sources, okay, do you think you can make them exactly identical? So, if you attempt to make two identical current sources, two independent identical current sources, right, there will always be a small mismatch between them, right? Either this current source is, this current is larger than this current, or smaller than this current, okay, or with a vanishingly small probability the two of them are equal. Even if they are equal, it does not really help us because we still do not know what the potential is, correct. So, let us consider the situation where this is slightly smaller, larger than the push up current is infinitesimally larger than the pull down current. What do you think will happen to the potential of the node? It will keep increasing, okay. So, if this current is larger than I naught, then the potential at this node will go on increasing, okay, all right. And on the other hand, if the push up current is slightly smaller than the pull down current, what will happen? The node potential will go on decreasing, okay, all right. And if the two currents are exactly the same, the node potential will stay constant. Is this clear? So, in other words, if this current is larger than the pull down current, this node potential will continue to rise. And how high can it go? In principle, it can go to infinity, but in practice, I naught is a current source made with transistors. And what kind of transistors do you think will be needed to make I naught? If you want a current pushing down, you must have a PMOS current, PMOS transistor operating in saturation. And when does a PMOS transistor operate in saturation? Only when the drain is sufficiently low compared to the source. You understand? Is that clear? So, if this potential keeps rising because epsilon is greater than 0, right, this potential goes on rising, what will eventually happen? The current source, which is made using PMOS transistors, right, will eventually have the lower terminal whose potential will start to approach the potential of the upper terminal, and the transistor, the corresponding transistor will go into the triode region where it no longer behaves like a current source. Does that make sense? Okay. All right. On the other hand, if epsilon is negative, in other words, the push up current is smaller than the pull down current, what happens to the potential? It keeps decreasing, keeps going to, and what will happen eventually? M1 will go into triode. After that, this current will go into triode, and bad things happen. Correct? Is this clear? And if I naught, these two happen to be exactly identical, that really doesn't mean anything because that potential is unknown. Okay, it could be at a potential where M1 is in triode, okay, and it could remain there because the current being pushed into the node is the same as the current being pulled out of the node. Does it make sense? Okay. Now, if I had to describe the same thing in terms of the complete circuit, what can I say? If the sum of the two currents on the top is not the same as 2I naught, what do you think will happen? I mean, these two potentials are the same. So the average of these two potentials is the same as the individual potentials. Correct? Okay. So if you didn't want to resort to this half circuit thing, right, what you could say was that if the sum of these two currents, the push up currents, was greater than 2I naught, then what will happen? The output common mode voltage, which is the same as either potential, correct, will keep going. If the sum of the two currents is greater than the pull down current, then the common mode potential will keep going up until the two push up currents get saturated or get pushed into the triode region. Sorry. On the other hand, if the push up currents, the sum of the two is smaller than 2I naught, then the common mode potential will keep dropping and eventually pushing M1 and M2 into triode. Okay. Only if I naught is the same, I mean the sum of the two push up currents is the same as 2I naught, which is the pull down current, then you can say that the potential or the common mode voltage at the output remains constant, but still we don't know what that constant is, and that could result in A, M1, M2 being in triode, or I mean if you assume that those two are current sources, then it's the only possibility is that either M1 and M2 are in saturation or in triode. You understand? So are we in a good situation or are we in a bad situation? Bad situation. Why are we in a bad situation? We have absolutely no idea what's happening, because the output common mode, which you want to be higher than what? You want the output common mode to be greater than VCM minus VT, so that M1 and M2 are both in saturation. However, at this point we have absolutely no clue what is happening, because we've chosen these two currents with the good intent of removing that I naught from the two currents of the differential pair. Correct? Why is this problem happening? We've chosen, why have we chosen those? What are these two currents doing here? Why do we need those two currents? We need those two currents because the branch currents or the drain currents of M1 and M2 are I naught plus something and I naught minus something. We want to get rid of I naught, so we put those two current sources there in good faith, right? But now we notice that even when the input differential voltage is 0, where we hope that the drain currents, the drain voltages of M1 and M2 are high enough to keep them in saturation, we see that even if there is an infinitesimally small mismatch between the push up currents and the pull down currents, we see that the output common mode either keeps going up or keeps going down, or we have absolutely no idea what it is if it is constant. You understand? Okay. Alright. So this is the problem. Whereas ideally we'd like the output common mode to be at a known potential, which hopefully we can control. Okay. And that known potential must be a value which is greater than VCM minus VT. Correct? Okay. So why is the problem there? We know now we have a problem.
Because you cannot determine the voltage across the current source.
Yes. So we have a problem.
Because two currents are
Pardon?
The two parents are fighting against each other.
Okay.
Immanent cannot be.
Okay. The fundamental reason why
Can't determine the voltage actually.
yeah, so if you have okay, you have a node whose potential is being controlled by two current sources, two independent current sources, okay, then clearly that's not possible, right? So two independent okay, two independent current sources can never control the potential of a single node, correct? Because if I1 is larger than I2, this potential keeps going up to infinity. If I2 is larger than I1, the potential of the node goes to minus infinity, okay. Only if I1 equal to I2, the node potential remains constant, but we don't know what that constant is. So in other words, if you had two independent current sources, the node potential is not a well defined quantity, correct? It's like somebody being controlled by two bosses, right? Boss 1 says no, you do this, and then boss 2 is completely independent, right? If they were talking to each other, then things work, okay, because this guy says no, I told him to do that, and the guy understands and then doesn't give him any more work, right? On the other hand, if one guy says no, you go and finish all these circuits today and come back to me tomorrow, and the other guy says no, that's all crap, just go and do me design these circuits and come back, what is the poor guy going to do? Going to go crazy, correct? Okay, so two independent, no person can have two independent bosses, right? If the person is to be stable, you understand, correct? So now we know the problem. So what is the solution? The two bosses are not talking to each other. That's the problem, right? So what should you do? They should talk to each other. In other words, one boss should be controlled by the other. You understand? In which case the guy is no longer a boss, though he thinks so. Huh? You understand, right? So two independent sources cannot control. Two independent current sources cannot control a given node. So obviously, if the node has to have a well-defined potential, one of the currents must be made dependent on the other. Okay. So the solution all right. You understand? Okay. So before we get into the differential pair, let's figure out how we might want to make this work. So you have two guys who are trying to control the potential of this node, correct? So now it's completely up to us whom we want to make independent and which current you want to make dependent on the other. So all that we have said so far is that both these guys can't be independent. So we choose, let's say, this guy to be independent, right, and this character to be talking to I0 in some fashion, correct? Okay. So if you want this potential to be constant, at some Vref, for example. Okay. All right. What do we do? Let's say this is some I1. I mean, if this guy is dependent, it can't be a simple current source like this. It must have some control knob. Okay. All right. And if you want this node potential to be Vref, what will you do? So what you will do is, if this potential is rising, what does it mean? The current being pushed into the node is higher than the current being pulled out. On the other hand, if this node potential is falling, then it means that the push in current is too small and must be increased. In other words, what I must do is to look at this difference, okay, and then control this current source in such a manner that this voltage remains constant. Correct. Please note now that the only constant that this potential can be is Vref. Okay. You understand? In other words, if this voltage is smaller than Vref, it means that the push in current is too small, right? So this guy will go and kick this current source to push in more current. The voltage will keep increasing. The moment it reaches Vref, these two potentials become identical, which means that this stops pushing the current source, and by definition, therefore, this current must be I naught, because this potential is not changed. Is this clear? Okay. So you can see that therefore, whatever happens to this current source, once everything is settled, this current, the push in current is exactly equal to, yes, what? The pull down current. Okay. So this current is now dependent on this current. Yes, and it's always equal to I naught. Okay. One could also conceive of the opposite situation where the push up current is fixed and the lower current source is controlled, and it's controlled based on the potential at the junction of those two current sources. Does it make sense? Okay. Now let's get to transistors one by one. So if you want a variable current source, what is the simplest variable current source which you can push in, which pushes current that you know? Yeah, transistor. What kind of transistor? I want current to be pushed in like this, a PMOS. Okay, all right, and this is my I naught, which is the control node, the gate. So if I increase the gate potential, what will happen to this current? It reduces, okay, and vice versa. So if I want to keep this potential at Vref, what should I do? No, assume you have an ideal op amp. Okay, you compare this to this. If this is higher than Vref, what does it mean? Okay, let's put the arbitrary signs for the op amp. If this potential is higher than Vref, what will happen here? This will go up. But if this potential is higher than is going up, what does this mean for this current source? it's too high, correct? So what must I do to the gate? I must reduce the current, which means that I must reduce the source gate voltage, which means that I must increase the gate voltage. So does it make sense? Okay. You understand? All right. So this way, this potential is set at Vref without any ambiguity whatsoever, right? Please note that this would not have been possible if the two current sources had been independent, okay? Because an infinitesimal difference between the two currents would have pushed the node voltage either to plus infinity or minus infinity in principle. Okay, now let's get back to, yes. Oh, you have exam, yeah, you can be. Okay, so now let's get back to this character here. What is the time? Oh, it's 4. Okay, we'll continue in the